So we're in section 9.2. We're going to talk about secants and tangents. Let's put the electronics away, please. Secants and tangents. So secants and tangents are special lines that have some, when they intersect circles, certain things happen. So let's first talk about what a secant and a tangent is. A secant is a line. So there's only three possibilities with lines and circles. The line either doesn't go through the circle, it goes through the circle, and when we're on the plane, it goes through the circle twice, or goes through the circle once, or it touches the circle once. So that's our possibility. The line doesn't go through the circle at all, it's not that interesting. So a secant is a line that intersects a circle in two places. So that's one of the lines we're going to be talking about, is the line that goes through the circle twice. So it goes across the circle. And a tangent is a line that intersects a circle in exactly one point. So secant goes through the circle twice, a tangent just touches it once. So let's draw a quick picture of a secant and a tangent. So there's our circle, and our secant line is going to go through like so, and our tangent line is going to look like that. So the secant is going to touch two places, tangent in one. So that's our secant line, and that's our tangent line. Secant comes from Latin, means to cut. So the secant line cuts through the circle. Tangent line, Latin again, means to touch. So the tangent line just touches the circle. So that's where the words come from. Tangent lines in math are really important. If you go further in math, tangent lines to curves. If you have a graph, talk about the line that touches the graph in just one place. That turns out to be a really important idea. So the tangent line is something that comes up over and over and over in math. And in calculus, the tangent to a graph is one of the most important ideas that we talk about in calculus. So if you go further, the idea of a tangent is really important. So we get to start working a little bit with that today. So those are the two kinds of lines that we're going to work with today. Notice the secant line where it cuts through the circle. The segment between the 2 points where it cuts through the circle makes a chord. So a secant line is going to cut through a circle, and it's going to leave us a chord for the segment between the 2 points where it touches the circle. They're related to chords. So the first thing we want to know is what happens with a tangent line. What happens with a tangent line in a radius of the circle? So let me grab this. I have a little demonstration so we can make a prediction about what's going to happen. So what we have with this demonstration is I have a circle. Right now we have a secant line that goes through the circle, and segment AB is a radius. No, we'll draw a picture in just a second. So this is just to kind of get an idea of what we're talking about. And measure of angle ABC. So we're measuring this angle between the secant line and the radius. And what we want to do is we want to predict, we want to think about what's going to happen to this angle as point C gets closer and closer to point B, and rather than a secant line, we have a tangent line. So right when C is sitting on top of B, we want to figure out what's going to happen to that angle. So right now it's pretty small. So as we move closer, anybody want to guess what they think is going to happen? To the angle.
It's going to become a tangent.
It's going to become a tangent. And what's going to happen to this angle? Gets bigger.
90.
So one person predicts 90. Anybody else want to make a prediction? So we're getting closer and closer. C's getting closer and closer and closer. Now we went past. So that's about as close as I can get it. So point C is sitting right on top of point B now. So now rather than a secant line, we have a tangent line. And the angle is 90 degrees. About as close as I can get it to 90 degrees. And I can make the circle smaller and do the same thing. I can make the circle bigger and do the same thing. Right when C is on top of B, we're at about a 90-degree angle. I can, and it doesn't matter where I put the radius on the circle. I could do it around here and do the same thing. Bring C around, and when they're on top, it's right at 90 degrees. So what we're seeing here is that when a tangent and a radius meet at the circle, they make a 90-degree angle. Doesn't matter how it's arranged, how the circle is arranged. When we have a tangent line and it meets the radius, the angle is going to be 90 degrees. So that's going to be our first theorem that we're going to talk about today. That's the tangent. Turned it off. So our tangent theorem says that if a line is tangent to a circle, then it is perpendicular to a radius
Out of underneath.
Yep. There we go. Oh, the pen's out of batteries. Okay, you want me to do it now? All right, then it is perpendicular to a radius on the circle. So the radius and the tangent have to meet in order for this to work. So if we're tangent to the circle, if the line's tangent to the circle, then it's perpendicular to a radius on the circle. So our picture for this is going to look like what we just saw. So there's our circle. I draw in our tangent line. And we'll draw a radius to there. And that's going to make a 90-degree angle. So if you have a tangent line, the tangent and the radius where they meet on the circle makes a 90-degree angle. So that's our tangent theorem. And this is going to show up a lot when we're working with circles in this chapter. The idea that a tangent and radius make a 90-degree angle. Questions on that example or that theorem? All right, let's look at another demonstration. So now we're interested in what happens. So we have a chord, we have a secant line that makes a chord in the circle. What happens with the chord and the radius? So here I have this this chord. And what we're measuring on this one is the angle between the radius and the chord, and the length of this segment from B to E, and the length of the segment from E to C. And what we're interested in on this particular demonstration is what happens to the length, how do the lengths of these two, from D to E and from E to C, how do they compare when that angle is 90 degrees? Let me make the circle, move it over here a little bit, make the circle a little bigger. So right now, those two lengths are fairly different. So what do we think is going to happen as this angle gets closer to 90 degrees? How do we think this length from B to E is going to compare to length E to C? It's going to shrink. Anybody have any prediction of how they're going to compare? So when this angle is 90 degrees. Someone says they're going to be the same. Now they're getting closer, right? So that, I'm not sure I can get it any closer than that. There's about as close as I can get. So now the angle is 90 degrees, and the length from here to here is the same as the length from here to here. So the radius is perpendicular to the chord, and the chord is cut in half now. So this segment is cut in half. I could shrink the circle and do the same thing. And if I make that angle 90 degrees, they're going to be the same. I can move the chord around and do the same thing. Make the angle 90 degrees. And they're going to be the same. So no matter what I do to the circle, if the chord and the radius meet at a 90-degree angle, the chord is going to be cut in half. So that's going to be our next theorem. And we're going to call that the radius and chord theorem. And the radius and chord theorem tells us just what we just saw. A radius that is perpendicular to a chord bisects the chord. Remember, perpendicular means 90 degrees. Bisect means cut in half. So there's our circle. We'll just draw a picture. This is going to look just like our demonstration just looked. So here's our radius. Here's our chord. This is a 90-degree angle. And those two lengths are the same. Does anybody have an idea, just looking at this picture, how we might prove this theorem? How we might show that if that angle it definitely has to do with triangles. So what we would do to prove this, we know that this is a 90-degree angle. What we're going to do, and I'll do that in green, is we would draw in these two radii in green. What do we know about the radii of a circle? What do we know about the lengths? They're always the same. No matter where I draw the radius, the lengths are going to be the same. So this green segment is congruent to that green segment. They're both radius. And now we have a right triangle, and we have a hypotenuse. And this side is congruent to itself. So we have a hypotenuse and a leg, and a hypotenuse and a leg. So the two triangles are congruent. So all the parts have to be the same. So that's how we would go about proving that. The reason that I wanted to show you this is because that's something that's going to happen often in Chapter 9, is that a problem that has to do with circles turns into a problem that has to do with triangles. And if we can't figure out how to solve the problem, we can draw in a radius that can be helpful. Because a radius, we know that any radius of the circle is the same as any other radius. So that often comes in to solving problems in this chapter. So I wanted to show that with this little thing. So let's look at an example using that idea. So here's an example using the radius and coordinate. So here's a circle. With that in black. And we'll draw in the radius. And my drawing's not going to be the scale, just so you know. And that's a 90-degree angle. And we'll call this P, this R, this A, this B, and the point here in the middle is X. And we know that PX is 6, and AB is 10, and we want to find the length of the radius. So we know that PR, we want to figure out the length of PR. Let's label what we know. This piece from P to X is 6. This is a 90-degree angle, so what do we know about what the radius does to the segment AB? It bisects it. So how long is it from X to B? Same as X to A, and which is going to be 10, 5. The whole thing is 10, so half of it is 5. Anybody see what we can do now? What was our helpful hint just a second ago? Draw a radius. So I'm going to draw a radius. And I want to draw a radius that's going to be helpful. I could draw a radius anywhere. I want to draw one that's going to be helpful. How about this one? How about that radius? It's the same as this radius because they're both a radius. What kind of triangle do I have here? Could be a 30, 60, 90, but do we know the angles? We know a 90-degree angle, so it's a right triangle. Pythagorean theorem always works on a right triangle. What side is the radius here, A, B, or C? Has to be the hypotenuse. It's the longest side. the opposite the right angle. So that's side C. So I know that C squared equals 6 squared plus 5 squared. So C squared equals 36 plus 25. C squared equals 61. So C equals the square root of 61, which when I plug in my calculator is approximately 7.81 units. So this kind of thing comes up often in chapter 9, where a problem that has to do with circles turns into a problem with triangles. And in order to solve it, in order to figure it out, we draw in a radius that's going to be helpful to solve our problem. Turn our circle problem into a triangle problem, draw in a radius to help us out. So that happens often in this chapter. And that happens often when we're working with circles. Question on that example. Okay, one last thing to talk about. The converse. Converse of the tangent theorem. So let's remember what a converse is. If we have an if-then, what do we do to get a converse? Switch them around. So let's go back to the tangent theorem. Our tangent theorem said if a line is tangent to a circle, then it is perpendicular to a radius. So how do we switch that around? Not a radius is perpendicular to a circle. If a line is perpendicular to a circle, then it is at a radius, then it is tangent to the circle. So the converse is going to say if a line is perpendicular to a circle, to a radius on a circle, then it is tangent to the circle. So we're just switching the direction. And it turns out that the converse is also true. We're going to say if a line is perpendicular to a radius, on the circle, because we want it to be perpendicular right where they touch, not somewhere in the middle of the circle. So it's perpendicular to a radius on the circle, then it is tangent to the circle. So we can figure out about the tangents going either direction. And our drawing looks just the same as the other one we made. We have a tangent and we have a radius. So if we know that the radius and the tangent, the radius and this line are perpendicular where they touch, that tells us that it's a tangent to the circle. It only touches the circle at that one point. So the main things, the big things that we want to take away from this section. The line is tangent to a circle, makes a 90-degree angle with the radius at the point where the line touches the circle. If we have a radius perpendicular to a chord, 90-degree angle, it cuts the chord in half. So those are the main things that we got from the secants and tangents. And then the other thing to remember is circle problems turn into triangle problems, and you can draw a radius to help you solve the problem. Questions? Okay.